Hello everybody, this is Dr. Christopher White, and in this presentation we're going to continue looking at plate tectonics. So in this particular presentation we are going to look and think about some of the evidence that we have which supports the idea that the Earth's surface is split into tectonic plates that are all moving relative to each other. So this is going to correspond to section 3.3 of your textbook. Now, before we do anything, we need to think about the idea of continental drift. So, as soon as we come to the conclusion that the continents were once joined together and they have to migrate to their current positions, well, as soon as we accept that, we must therefore also accept that the surface of the Earth cannot be one solid sheet of rock. If that was the case, if it was just one solid sheet, well, the continents would never be able to move relative to each other, so continental drift couldn't happen. So the fact that we can see the continents, or at least we have the evidence to suggest the continents are moving, is a strong indicator that the surface of the Earth must consist of individual plates of rock which are all moving relative to each other. And of course this means sometimes the plates will bump into each other, sometimes the plates will move away from each other, and sometimes the plates will simply move past each other. So as soon as we accept this idea, all of a sudden some of the topographic variation that we can see on the surface of the Earth begins to maybe make a little bit more sense. So if we look at our map of the Earth here, what can we see? Well, we know that we have these mountain belts. Well, if you think about what's going to happen when you have two very, very large pieces of rock smashing into each other, it's going to cause a lot of deformation, isn't it? So think about it as two cars crashing into each other head on. There's going to be an impact, and where the two cars meet, you're going to have the crumple zone where everything gets deformed because of the force of the impact. The same thing is going to happen to the crust. So if we think about the Himalayas, and if we were to imagine a situation where India was moving northwards and it smashed into Asia, well, the crumple zone, essentially the area of deformation, is going to be right here, where we have the Himalayan mountains and the Tibetan plateau. In the case of South America, it would be the continental crust of South America being hit by the oceanic crust off to its west. Same thing along the western coast of North America, and also along the mountains of the Mediterranean here. We have Africa would be crashing into Europe, and that's essentially producing the mountain range that we can see here. The mountains we can see here would be the result of the Arabian Peninsula hitting Asia. So we can see that all of a sudden, if we accept that the continents are going to crash into each other, then we may have an explanation to explain mountains. So what about our ocean basins? Well, we know that we have these rifts which are running straight down the middle. Now, if we assume that South America and Africa were once joined together, and we have evidence that would suggest that was the case based on the jigsaw fit, the fossil evidence and the glacial evidence, well, that would mean over time South America has moved one way, Africa has moved the other way, and so that means we obviously have to be making new crust to fill the space as they move away from each other, don't we? And all of a sudden that begins to explain what this ridge is that's running down the middle of these ocean basins. It represents the point where two plates are moving away from each other, creating a rift through which magma can rise and form new crust. So all of a sudden things are beginning to make sense. In the case of the mountainous terrain here, we've already discussed about how the mountainous terrain may well be an indicator that we have, in this case, oceanic crust hitting continental crust, creating the mountain range. But you'll also notice there's that trench. So that would suggest that maybe this collision is also leading to the formation of this trench on the seafloor. Now that would mean over here by Japan, where we have a piece of oceanic crust hitting another piece of oceanic crust, well, that would suggest that the trench which is forming there is also the result of two pieces of crust banging into each other. At the same time, when we look at pieces of continental crust which are well away from the boundaries, what we can see, for instance, if we look at the centre of Asia and Europe, if we look at Australia, if we look at Central Africa, Eastern South America and Eastern North America, we can see that these areas which are well away from these boundaries are geologically quite inactive. They're relatively flat, lowland areas. And so this would suggest that the boundaries here are very geologically active. They're leading in some cases to the deformation of the rock, creating features such as mountain ranges, whereas areas which are away from these boundaries are on the whole geologically quite quiet. So obviously we've already discussed the difference between oceanic crust and continental crust, so we don't need to worry about that. We've discussed how mountain belts may well be due to some kind of collision. We've also shown that the mountain belts seem to be related to trenches, which would also suggest therefore that trenches are the result of collisions. We've also discussed how when your continental crust is well away from your plate boundaries, it appears to be less likely to be deformed. And we've also discussed how this high ground may well be related to collisions. Now, in the case of the high ground here in Africa, there's going to be another explanation which is going to be better explained in a future presentation. So next we're going to look at earthquakes. And when we look at earthquakes, we suddenly spot a very obvious pattern. I dare say you saw it the second I flicked to this slide. You can see that earthquakes like to form linear chains. These chains of earthquakes are marking out the locations of the plate boundaries. Because think about it, if two pieces of crust are smashing into each other, that's a lot of tectonic force on the rocks. That's going to create earthquakes. When two pieces of crust are being ripped apart and moving away from each other, that's also going to create quite a lot of earthquakes. When pieces of rock are moving past each other, well, once again, there's going to be lots of earthquakes due to the friction of two pieces of rock trying to slide past each other. So all of a sudden, we can see that these earthquakes form these linear chains. And so now we can use these to help to guide us towards the location of the plate boundaries. And if we just look back in the previous image, we can begin to see things like, for instance, here's our ridge running down the middle of the Atlantic. There it is there, marked out by the earthquakes. We have this ridge running along here, essentially between Africa and Antarctica. There it is marked out there. We have essentially the plate boundary here between the oceanic crust there and the continental crust here. Here's our mountain range, the Andes, and once again, we can see that it's a very, very earthquake-rich environment. Now, once again, just like the topography, the further you are away from a plate boundary, the less likely you are to have earthquakes. So if we look at Central North America, Central South America, Africa, Central Europe and Asia, we can see that these areas which are well away from a plate boundary are relatively earthquake-free. The final thing that we need to note is the thickness of the band of earthquakes. So you'll notice in some cases the earthquakes form these long linear chains like this ridge running down the middle of the Atlantic. However, in some cases like the Andes, you can see that the region of earthquake activity is a lot wider. And so this may well be related to the type of event that's taking place. Here in the Mid-Atlantic, we've discussed the possibility that this could represent where two pieces of continental crust are, well, two pieces of crust, sorry, I do apologize, two pieces of crust are moving away from each other. Now, this could lead to the formation of a thin, narrow band of earthquake activity. In contrast, where we have pieces of crust smashing into each other, like along the western coast of South America, well, that could create quite a broad region of deformation, and that's going to lead to a broad region of earthquake formation. The final thing is that where we have these isolated earthquakes over here, well away from boundaries, so here we have the Hawaiian Islands, these are probably due to magma moving through the crust. We know this in the case of Hawaii because we know it's very, very volcanically active. And so this volcanic activity here is probably not, well, sorry, this earthquake activity here is probably not related to pieces of continental or oceanic crust interacting with each other. It's probably due to magma movement. And the same goes for areas like the Galapagos Islands over here, or some of these smaller island groups in the middle of the Atlantic. They're related to volcanic processes which aren't directly related to plate tectonics. So they're slightly different in their origin. So if we look at this map here and then we combine it with the next map, or I should point out, sorry, we have a few highlighted points here. So we have belts of earthquakes. We can see these linear features. We can see some of them are associated with these rifts running down the middle of the oceans. We can see some bands of earthquakes are associated with trenches and mountain belts. and we can see that we have areas where there's sparse earthquake activity, and those are normally quite a long way from the plate boundaries. So now let's look at volcano activity. So what can we see? Well, the first thing that we'll notice is if we look at these ridges running down the middle of the oceans, we can actually see they're surprisingly volcano-free. So if we look at the Mid-Atlantic ridge, which is running down here, you can see on the whole there's not much volcanism. We can see there's a lot of volcanism here related to Iceland, but that's not actually due to plate tectonic processes. That's due to another reason called a hotspot, which is situated directly below Iceland and is feeding the volcanoes at the surface. And you can see we have other small clusters of volcanic islands, once again related to hotspot activity, but the actual ridge itself is relatively volcano-free. Same for this ridge here, same for the ridge we have coming along here, same for the ridges we have over here. You can see they are relatively volcano-free. In contrast, where we have, I'm just going to skip back a couple of slides, where we have these trenches, you will notice there is lots of volcanic activity. So here we have a trench that's running all the way down here. You can see it quite clearly on the map there. Look at all of these volcanoes. Same over here. Here's another trench running along the southern coast of Indonesia. There's a line of volcanoes right there. On the western side of South America, there's our trench. Here's our line of volcanoes. Western side of North America and also the Aleutian Islands. There's our trench. Here's our trench here for the Cascade volcanoes. And once again, we have corresponding volcanic activity. So it would seem that the trenches, the areas where we may have pieces of crust smashing into each other, could well be associated with volcanic activity, and that would suggest that the process of pieces of crust smashing into each other leads to rock melting, producing magma which feeds volcanoes. But at the same time, we also spot a couple of other features which are quite interesting. Here are the Himalayan mountains. Notice, relatively volcano-free. So hold on a second, we have a bit of a problem. If we're saying that the Andes are being created by two pieces of crust smashing into each other, that leads to melting, which leads to magma, which leads to the formation of volcanoes. Surely the same the same system should operate with the Himalayas. If I'm claiming that India is hitting Asia, then I should see exactly the same thing, shouldn't I? I should see the mountain range, I should see the earthquakes, and I should also see the volcanoes, but I don't. So something is clearly happening here, well, something is clearly not happening here, which is happening over here, for instance. So we need to make sure our model is refined a little bit to take into account these differences. We can also see down here along the eastern side of Africa that we can see we have a line of volcanic activity here, which is actually associated with an area, if I just go back to the first picture, which is relatively topographically flat. So once again, we need to explain why we have an area which is topographically appears to be relatively geologically inactive, but from an earthquake, so you can see it here, and volcano perspective, it's actually quite geologically active. So there are a few questions which we need to answer, and we will do so. So what we can see is using topographic data, using earthquake data, and using volcanic data, we can begin to see the boundaries between these plates which have to be present if we are going to believe that continental drift is actually happening. All right, everybody, thank you for watching the presentation and have a good day.